Okay, well, first of all, I would like to thank the organizers for giving me this opportunity. So today I'm going to talk about numerical relativity beyond astrophysics, and I'll try to explain what type of problems we encounter and why this is challenging and interesting, especially for a broader community like the one coming to this workshop. So the first question one might ask is, after the detections of gravitational waves, why should we care about, studying general relativity beyond the astrophysical setup, because this seems to be the interesting setting. And I'll try to argue in this talk that there's plenty of interesting problems outside the astrophysical context, which of course for an audience of mathematicians that's absolutely fine. So firstly, when one considers, so why gravity in this new setting? So firstly, from the point of view of high energy physics, and in particular from the point of view of more fundamental theories of gravity, such as string theory, high dimensions or exotic spaces arise very naturally. So that's one setup. And another reason why one wants to consider gravity here is because one might be interested to asking the same questions that we are interested in the astrophysical setting. So for example, physics of black holes, gravitational collapse, or these weak and strong cosmic censorship conjectures, which are important open problems in GR. So one can address the same questions in other settings and actually learn more about the fundamental aspects of the theory, namely general relativity. It turns out that when one considers gravity in high dimensions or in exotic spaces, then black holes can have very different physical properties than the usual ones. So for instance, they can have non-spherical topology, or even the spherical black holes, when you put them in this exotic space, ADS, which I'll tell you more about, they can have completely different physical properties than the astrophysical black holes. And another common feature are gravitational instabilities. So these black holes, even in vacuum, without the presence of matter or anything, they can be unstable under gravitational perturbations. And understanding the dynamics of these instabilities and their endpoints is actually quite interesting. And it turns out that ADS itself can be non-linearly unstable. But also, it turns out that when one considers gravity in untitled Chapter space, one can connect gravitational physics to non-gravitational physics, which is relevant for particle physics, in particular for understanding the outcome of, say, some experiments that are taking place currently in like the LHC, in these heavy ion collisions and so on. And this has led to interesting developments in relativistic fluid dynamics in recent years that could actually be relevant also in gravity, in particular for neutron star simulations. And recently it's been realized that when you take the number of space-time dimensions to infinity, the Einstein equations simplify enormously, to the point that one can try to address like the usual problem, say black hole binaries or physics of black holes, in an analytic or even using just soft numerics, like just solving simple equations in laptops. You can try to address the same question, and you can get some interesting, useful insights from this expansion. And in fact, this is also perturbative expansion. You can actually make a lot of progress using analytical techniques. So when one considers gravity in these settings, then there are the following common aspects of the dynamics. So firstly, there are strong energy cascades to the UV. And black holes or gravitational physics can be described, or is often described, by multiple relevant length scales. This should be contrasted to the traditional black hole binary problem in vacuum, where there are essentially three relevant scales, which is the wave zone, the orbital scale, and the size of the horizons. And one can accurately simulate the system, as we heard in the first talk of this conference this morning, by just using a fixed mesh hierarchy. And as long as you resolve these three relevant scales, then you are good to go. That's no longer the case in these high dimensions or ADS, where there are several scales that you need to resolve. Some of them arise as part of this strong UV cascade, and you need to resolve them. And the process can be actually random. So fixed mesh refinement doesn't work here. And we will see examples of this. So the rest of my talk is organized as follows. So first, I will provide a review of the various methods that are now used in solving the equations numerically. And then I'll walk you through some of the challenges that we encounter through two examples. So first is the dynamics of these unstable black holes in higher dimensions. I'll discuss a couple of examples. And the second part, I'll discuss dynamics in ADS, in particular gravitational collapse in ADS, how we approach the problem and what the challenges we encounter here. And I will finally summarize and conclude. Before I start, I must say that all I'm going to talk about has work that I've done with these linear combinations of these collaborators, some of which are PhD students that passed to a better or maybe a different life, let's say. And all it's just ongoing work. And also it's part of a collaboration, which is GR Chomo. There's been a lot of hard work in terms of code development. And of course, I'm grateful for the support and help and fun collaboration. And this actually has allowed us to parallelize, vectorize the code to the point that we can run now efficiently with like 20,000 cores or so, which these computations I'll describe are quite intense. So we do need like good scaling, both weak and strong scaling. All right. So let me start with just a flash review of the methods, mainly intended for those of you who are not very familiar with numerical relativity. Those that are numerical relativity experts, you will not learn anything new. All right. So first of all, I will consider only the vacuum case, just to keep things as simple as possible. And in these new settings, it is very useful, or I would say almost essential, to add these constraint damping terms to the Einstein vacuum equation. So these, here we've got the Ricci tensor, and there we add this vector z, whose components are essentially the constraints. So we, the continuum level, we are just adding zeros to the equation. Doesn't really matter, but of course numerically, due to truncation errors, those terms matter, and they matter a lot. And in particular, they allow you to give a finite speed of propagation to the constraints, and by carefully choosing these three parameters, kappa 1 and kappa 2, one achieves that these constraints are actually exponentially suppressed. So adding these terms is very important to make sure that your code is stable. So in the, again, traditional vacuum case in the 4 dimensions, you don't really need to add these terms, but in high dimensions or ADS, it's essential, I would say. As I said, I will only consider the vacuum case. There are other systems with a lot of interest, namely neutron stars, that pose challenges of their own, but I will not discuss them here, mostly because I'm not an expert of this. But I want to point out that in recent years, there's been some interesting developments, particularly in finding new versions of relativistic viscous hydrodynamic, which are well posed, and that's potentially relevant for neutron star simulations, and even new formulations of magnetohydrodynamics. Some of these developments have been inspired from high energy physics, in this case based on higher form symmetries, and those could be relevant for simulating these systems. But as I said, I will not discuss this here. And just to emphasize that these are very complicated systems that have posed challenges of their own. So the first approach is the well-known ADM approach. So one just writes down the space-time metric in this way. So just foliates the space-time in space-like hypersurfaces, and on each hypersurface you have the induced metric and the second fundamental form, which is essentially the time derivative of the metric. So the Einstein equations provide evolution equations for these two objects, and then these parameters, the lapse and the shift, just determine how you embed this hypersurface into the full space-time, and there's a freedom to do that. So basically, the freedom to choose coordinates is encapsulated in specifying suitable evolution equations for these two variables. And as is well known to any GR practitioner, just choosing good coordinates is essential to actually solve the problem. So as we saw in the first talk today, just finding good evolution equations for these two variables was crucial to crack the black hole binary problem using this formulation. As is also well known, just the equations you get for these two variables are not strongly hyperbolic, so they're not suitable for numerical evolution, and this is now well understood. So the way forward is to just reformulate the system of equations in terms of new variables. So firstly, one pulls out just a conformal factor, and this is useful because in the traditional case, there is a coordinate singularity in the domain, and basically the singularity is hidden in this variable. So all the other variables are smooth. One also splits this second fundamental form in terms of the trace and the trace-free part. But crucially, we have two new variables. One is, this is essentially the time component of this vector z. They added to the Einstein equation. This encodes the Hamiltonian constraint. And then there's this other variable, which involves this contraction of the Christoffel symbols. This is critical to change the second derivative structure of the Einstein equations, turning the system into a strongly hyperbolic one. And that's basically a momentum constraint. So in terms of these variables, one obtains a strongly hyperbolic system, which is suitable for numerical evolution. But I'm not going to write it down here because it's unilluminating and it's complicated. As I said, a very important point is to choose good coordinates. And it turns out that this is a good choice for these parameter labs. So what this evolution equation does to your hypersurfaces is to basically they accumulate near this, they all get pinned down to this asymptotic region. So they basically accumulate inside the horizon, just freezing the evolution inside black hole horizons and avoiding the singularity altogether. So in this formulation, you don't have any physical singularity in the domain. You only have coordinate singularities, and the behavior of the functions near this coordinate singularity is well understood analytically. So you know how singular functions are. But in practice, for computations, a coordinate singularity is a singularity. So it means that the gradient of your functions will be large near this region. And in the four-dimensional case, you only have to worry about mostly this variable conformal factor. The rest of the variables are smooth. Another important choice, so I should say that this is just a free parameter. In the four-dimensional case, it's typically chosen to be 2. But in high dimensions, you can just put it to whatever, so some other values, which are not very different from 2. So that more or less works. The other equation is for the shift. And what this equation does, essentially, it drives these contracted Christoffel symbols to 0. So essentially, this drives your coordinates on the spatial slices to harmonic coordinates in terms of the conformal metric. And these are good coordinates. And again, these are just free parameters that one can choose so that you get a nice, smooth evolution. The point is that with this choice of coordinates, as I said, you don't have any physical singularities in your domain, so you don't have to excise any region. And from the practical point of view, this makes it very easy and convenient to implement. So you can decouple the problem of solving the equations from the problem of finding the apparent horizon. So the latter you eventually have to do. After all, you are interested in black hole physics, so you want to know what black holes do, what shapes they have. But these two problems, in principle, in this formulation are decoupled. And this is important, as we shall see, when one goes beyond the astrophysical setting. The second approach was pioneered by Franz and others, is to choose harmonic coordinates. So basically, this amounts to choosing these vectors z that I added to the Einstein equation to just be this. So your space-time coordinates satisfy just wave equations with some source functions. And the freedom of choosing coordinates just is encapsulated on the choosing cleverly these source functions. And in many instances, it turns out that choosing just harmonic coordinates works well. As part of this scheme, one excises the interior of the apparent horizon. So you have to find the apparent horizons as part of your evolution scheme. So that adds, and that corresponds to solving an elliptic equation, essentially. So that's another layer of complication. But in the four-dimensional case, this is really not a problem in practice, and this scheme actually works very well and is used extensively now in the community. One great advantage of this formulation is that the equations are just basically nonlinear wave equations. So understanding boundary conditions is straightforward. In particular, one can impose, for example, if you have a finite domain, you can impose outgoing wave boundary conditions, and this preserves constraint. In the previous formulation that I alluded to, this is much more complicated, and finding constraint preserving boundary conditions is very non-trivial. And as you go away from so the astrophysical setting, and in particular in ADS, where one cannot get away imposing approximate boundary conditions, then this formulation turns out to work very well. So I should say that in a symplectically flat space, even if you don't impose constraint preserving boundary conditions, as long as your outer boundary is sufficiently far, then it has little or no influence into your system. So you can get away with that pretty much. And that's also true in high dimensions, where decay of the functions is even faster. But as I said, in ADS, you don't get to choose. So you have a boundary, so you have to impose the correct boundary conditions there. Otherwise, you are not solving the equations correctly. And in this formulation, this is particularly easy and simple to implement, as I will describe later. Another issue is that, okay, I say we're going to simulate high dimensions. So, okay, how you do that? This is expensive. So it turns out that in many systems of interest, one is interested in preserving some symmetry, right? So, for example, say your black hole has some transverse sphere, and you are interested in preserving that symmetry just because the physics of interest just happened in the transverse directions. So you can reduce the cost of the computation by imposing these symmetries directly. So, for example, if you have, say, 4 spatial dimensions, so 4 plus 1 dimensional space, with a U1 symmetry, instead of solving the system into the full 4 spatial dimensions, one can solve the equations on a 3-dimensional slice, and then just rotate this slice using the symmetry to construct the full space-time. So at the practical level, what one does is, since you have, say, in this case, a U1 Killing field, then just by taking pseudo Lie derivatives of your fields, you can compute the transverse derivatives in terms of the derivatives on your computational domain. So if you do that, you can implement this at the level of the equations. You get some singular terms just because this effectively becomes an axis of symmetry. But again, the boundary conditions there are well understood, just standard regularity boundary conditions. And this reduces the computational cost of the problem, basically making it the same as in the standard 3 plus 1 dimensional case. Okay? This method goes under the name of the cartoon method. However, in these high energy physics applications, there is interest in simulating full 4 plus 1 dimensional spacetime in ADS. Right? So this is an issue that eventually we'll have to face. So there's no cheap lunch. So eventually we'll have to design codes that can cope with this dimensionality, and you can run it in a finite time with suitable, ordinary computational resources. So just to say that this is something that eventually one will have to think about. And there have been already some examples of simulations of this dimensionality, but it's still very limited, and eventually this should become standard. So eventually we'll have to deal with this problems of this dimensionality. Okay. So now I will consider just the first example, high dimensional black hole instabilities, and we'll see how what challenges arise in the setting which do not appear in the traditional astrophysical setup. So the first example, very famously, is that of the Gregory-Laflamme instability of black strings. So just to tell you what a black string is, you take your favorite 4-dimensional black hole, say the Schwarzschild solution, and you add a flat direction, which you then compactify on a circle of length L, so that the system has finite energy. So the black hole just will look like just a line like this. So every point here is, say, a 2-sphere, and these ends are identified. Okay, so this simple construction is a solution to the 5-dimensional Einstein equations in vacuum. And the thickness of this string is set by the mass parameter of, say, the 4-dimensional black hole, whilst the circle has asymptotic length L. very famously, Gregor and Laflamme discovered in the early 90s that when these black strings are sufficiently thin, namely when this dimensionless ratio is some order 1 number, then there exists a gravitational instability, namely a linear solution to the Einstein equations that grows exponentially in time and that breaks the symmetry along the circle, introducing some ripples. And for more than 15 years, there was a lot of discussion in the physics literature to know what would the endpoint of this instability be. The issue being that if you expect, perhaps correctly, that these black strings would break in finite time, there are theorems in GR that forbid this from happening in a smooth way. So if this black string has to break, a singularity must become visible in finite time. And this could be a counterexample of this weak cosmic censorship conjecture in such spacetimes. Right? So as I said, there was some discussion in physics, a lot of discussion, in fact, in physics for a long time, until Louis and Franz famously solved this problem using numerical GR. So they found, in solving the Einstein equations, that this instability evolves into a black hole, which is basically can be understood as a sequence of spherical black holes connected by long and thin necks. Each one of these necks is itself unstable. So this gives rise to a self-similar solution. And furthermore, they could argue that these necks would reach zero size, so they would pinch off in finite asymptotic time. So in finite asymptotic time, one would see a singularity. And this was the first counterexample of this weak cosmic censorship conjecture in such spacetimes. So, sorry? Yeah?
What's the relevance of 4D? I mean, I suppose it's not true for 3D?
No, because in 3D you don't have black holes which are asymptotically flat. So you only have black holes, asymptotically flat black holes in 4 dimensions, but not in 3 dimensions. So these cannot exist in 4 dimensions.
And then
higher dimensions, then it follows straightforwardly. Of course, then you can add more flat directions, and they're still allowed. They're still solutions, and then you could get more complicated dynamics if you allowed for dynamics in the various compact dimensions that you add. But this, so if you suppose instead of adding 1, you add a torus. That's also allowed. And then if you could consider perturbations on both of the compact dimensions, you could have more complicated dynamics. But eventually, the bottom line, the endpoint should all be the same. You would reach a singularity in finite asymptotic time, generically, unless you did some fine-tuning, which I don't see how this could save the day.
So you're just taking the Schwarzschild solution
Yeah.
in n dimensions and it's asymptotically flat.
Yeah. So that's, no, you could take the Schwarzschild solution in n dimensions is asymptotically flat. Then you could add another direction, and all of these would essentially follow, except you have to be in 13 or less dimensions. So the physics changes above 13 dimensions, because above 13 dimensions, it turns out that there can be stable solutions which are non-uniform. So then this breaking no longer happens in 14 and above. But for as long as you stay below 13, at least for the case when you have only 1 compact dimension, then this essentially goes unchanged. Yes. No. Total space-time dimensions, 13. That's the critical. No, in the case of d equals to 3, then this wouldn't work because you need to start with a black hole. So in 3 dimensions, there are no asymptotically flat black holes. So No. Sorry for the, so here I mean 4 dimensions. So sorry for the confusion. Yeah, no, it means 4 dimensions. Yes, but then just coming back to your original question, you could do 2 things. You could just consider high dimensional versions of Schwarzschild and just add flat dimensions, And then this is what would happen for as long as you stay up to 13 dimensions. But you could also start with the 4-dimensional Schwarzschild solution and add just more flat directions, which you then compactify. So that's also possible, and those would also be unstable, and presumably you would see very similar dynamics. But it would be a much more complicated computation because you have to allow for, you would increase the dimensionality of the problem. So this setting is the simplest possible one, which pretty much encapsulates the physics of this instability when you consider spacetimes with compact extra dimensions.
So the endpoint of this is a naked singularity, and now you're basically saying it's sort of a generic property. So is the idea then that cosmic censorship is just going to be some special property of four spacetime dimensions which are subgroups at all in any higher dimension?
That's quite possible. That this is the answer. That's quite possible. And I think this is one of the reasons why it is interesting to address these conjectures in these other settings, because then you get to understand what are the fundamental ingredients that could make it true. And this example shows that, and as we shall see in a minute, that these type of instabilities, and in particular these type of cascades, are generic as soon as you depart from the astrophysical setup. So just taking it from there, one can consider now asymptotically flat black holes in 5 dimensions or higher, which are non-spherical. So the first example of this are the black rings that were discovered by Roberto Empare and Harvey, which sits at the back of the room. And in 5 dimensions, they found an explicit solution. So you can write down, it's just a line. So it's not more complicated than the Kerr solution, for instance. And it's 5-dimensional, asymptotically flat, and it has horizon topology S1 cross S2. So these rings exist in 5 dimensions and higher, but they're only known explicitly in 5. So that's the case that we'll consider because it's just easier. Now, this is just the apparent horizon, or the horizon of this object. So that's the S1, and each point here on this circle is an S2. Okay? And as I said, they're asymptotically flat, and in order to be in equilibrium, they must be rotating along the S1 of the ring. They can also be rotating along the transverse sphere, but importantly, in order to keep them in equilibrium, they must have rotation on the S1. That's easy to understand, otherwise they would just collapse. I want to emphasize that this is asymptotically flat, so the topology of the space-time is trivial. So these rings, in particular, if they have some non-trivial dynamics, there's nothing preventing them from just collapsing into a black hole. Okay? In fact, it was realized rather recently that all black rings are unstable, and they suffer from different types of instabilities. And in particular, these authors discovered that there is one instability, which is essentially of the regular Flamm type. Okay? So it breaks the symmetry along the S1, introducing some ripples, and therefore, at the nonlinear level, this will lead to gravitational radiation. And in fact, they also showed that in the limit in which these rings are very long, so they look like black strings, indeed they could connect this instability to the regular Flamm instability of black rings. So the natural question to ask was, what is the fate of these objects? But in this case, I want to emphasize that these instabilities, because they break the symmetry along the circle that this ring is rotating, then this will lead to gravitational emission in the nonlinear level. So in principle, there's nothing preventing from these rings to emit gravitational waves, get rid of angular momentum and mass, and collapsing before they can actually break. So this was an open question. Another class of black holes that we will consider are rotating black holes in dimensions 6 or greater. These are just the analogs of the Kerr solution. The metric just looks exactly the same, just change. You add these in suitable places. And that's the case when you have rotation on a single plane. High dimensions, you can have rotation on several planes. But for simplicity, we shall consider only rotation on a single plane. So here, total space-time dimension 6 is relevant because it turns out that for d equals 6 and higher, these black holes can rotate arbitrarily fast. So the angular momentum is unbounded. There are always regular solutions to the Einstein equation for arbitrarily large but finite angular momentum. And it turns out that when they rotate very fast, then they look like pancakes. So they spread on the rotation plane. And unsurprisingly, it was found that when the rotation is sufficiently large, then they are also unstable under different types of instabilities. And again, one of these instabilities is of the granular flam type. In particular, there's one mode which just introduces ripples in the radial direction or in the angular directions as well, just making these pancakes non-uniform. So again, the question is, what is the endpoint of these instabilities? Yes?
I'm not sure why you call that a granular flam instability, though. It sounds more like a freezing strip instability. In particular, I mean, it's conceivable that all that instability of that sort does is to just spin the thing down where it's within a reasonable radius.
I think the instability you refer to is the type that was discovered by this gentleman, which breaks the symmetry. And what it does when the angular momentum is small enough is precisely what you just said. Just get rid of the extra angular momentum and spin it down to a stable solution. I call this other one granular flam because these objects near the rotation axis, when the spin is sufficiently large, they look like membranes. And you can connect these instabilities to the granular flam instability of a black membrane. So that's the reason. And as we shall see, the physics is essentially granular flam physics. We shall see this very briefly, but that's the reason. So there are different sectors, and they coexist, of course, at the nonlinear level. So I want to emphasize that even though in this talk I'm going to consider these two examples, black rings and black holes, these instabilities are generic in the sense that we know that in dimensions higher than 4, there exist many more types of black holes that are not known explicitly. However, all of them admit a regime of large angular momentum in which you expect large deformations. For example, black holes described by multiple largely separated length scales. And in this regime of large angular momentum, one expects them to all be unstable under this granular flam type of instabilities, because in this regime you can approximately understand, you can approximate the solutions by just branes or black members, black strings, all of these objects that we know are granular flam unstable. So as I said, even though I'm going to consider only two examples, then this is generic behavior of high dimensional gravitational physics. So why doing the simulations is harder than in the astrophysical case? So first is because we have large separation of scales in this regime of interest. So for example, these rings are all unstable, and where these potentially interesting granular flam type instabilities appear is a regime in which the radius of the ring is larger than the thickness or the size of the transverse spheres. So likewise, for these rapidly spinning black holes, these instabilities arise when the spread of the black hole on the rotation plane, which is set by the rotation parameter, is larger than the thickness, the size of the sphere in the transverse directions. So first of all, you've got large separations of scales to deal with. And this should be contrasted with the Kerr solution in 4 dimensions, that even if you go very close to extremality, then the horizon of the Kerr solution is not very much deformed from spherical symmetry. So it's really only described by one length scale. This is the mass parameter of the Kerr solution. This is not the case for these black holes, where you have several important length scales that describe them. And you need to resolve them. So the way we deal with this is, again, one has to adapt the gauge conditions to take into account that you have several scales that you need that are important at the horizon, and you need proper adaptive mesh refinement. So in this setting, having adaptive mesh refinement is not just something which is fancy and is nice, it's actually a necessity if you want to accurately simulate the dynamics of these objects. So just to give an example of one sort of grid setup that we used to simulate these black rings. So you can see have several levels of refinement with non-trivial topology to actually accurately resolve all the features of these black holes. And if you want to simulate the dynamics, then of course your mesh has to adapt to this object. And this is just an example of one ring which collapses into a black hole. So, and that's the only way you can accurately simulate these objects.
What number of dimensions are you computing?
So this is in 5 space-time dimensions with a U1 symmetry. So it's effectively 3+1 dimensional problem.
And what grid, what's that 2-dimensional?
So that's I'm showing this on the rotation plane, on a slice of the rotation plane that goes through the ring.
But you really have a three-dimensional?
Yeah. This is just one slice on the rotation plane at the equator of the ring. But it's a three-dimensional grid. So that's one issue. The second issue is that now this asymptotic region where, yes?
So in which way you control the mass refinements?
Sorry?
How do you control the refinements?
Yeah, so that's a very good question. So one needs to find an estimate of the error that tells you where you need more resolution. And what we did in this case is there's this function chi, the conformal factor of the metric. It turns out that in our working coordinates, this function tracks the apparent horizon. It tracks the shape. And one can use the gradients of this function to get a local estimate of the numerical error. So we use this as a trigger to, for our regrading function. And yeah, I don't have a deep understanding why this function works so well. Yeah, so I mean that's one of the issues. When you need why this is a good estimate. That, like I said, I don't have a deeper explanation, but it turns out that this function is very useful, as we shall see right now, actually. Yeah. Yes.
Yes, you're also moving the mesh. What is the strategy for moving the mesh?
I'm not sure if I understand. What do you mean moving?
Your mesh was adapting
Yes.
to the
Yes.
black hole in time.
Yes. Yes.
So you have probably a strategy for that. You're evolving the mesh.
Yes. After one can set up, you can, depending on the level, you can run your error estimate on that level and decide whether you need to add another level or not. And you can choose how often you do these checks. So we specify this. I mean, if you have if you've been in this business, there's some trial and error, because there's a compromise between efficiency and keeping the computation under control. So we do this for the finest meshes. We do this quite often because these are the ones that show the more dynamics. But for the coarser ones, you don't need to do this very often.
And you don't have a differential equation for the mesh.
No. Like I said, so the mesh follows this trigger function, which is one of our evolved variables. So we look at the gradients of this function as our error estimate.
So by the way, did you use any kind of things like interpolation?
Yes, of course.
What kind of interpolation?
This uses this. So this is our package built on Chombo, which is these adaptive mesh refinement libraries. So I think it uses this. It's fourth order interpolation, if that's what you're asking. We use a fourth order finite differencing scheme, and consequently we also use the same interpolation for the meshes, if that's what you're asking.
Yeah, anyway, so okay.
Yeah. So one issue is this the issue of singularity. As I said, in this formulation we use this ADM type evolution scheme. So we don't have a physical singularity in the domain. It's a coordinate singularity corresponding to another asymptotic region. And it turns out that in our working coordinates, this singularity is not just a point, which is what happens in the four-dimensional case, but here's extended. So for example, in the case of the ring, is a ring, like singularity. In the case of the black holes, it is a disk. So in practice, what happens is that now you have a much larger region of your domain which is under-resolved. Right? Because a singularity is a singularity, so we have finite resolution, have finite resources. So it means that gradients of the functions are large, and they are large on a larger region. So this introduces constraint violations, which, if you don't do anything about it, will eventually pile up and ruin your simulation. Okay? So that was an important issue. And again, one has to play with the gauge to make sure that the singularity just evolves together with the black hole. But more importantly, in order to keep the errors under control, we basically have to smooth out the functions near this region by introducing some diffusion terms. So let me explain this. So one issue is that in our initial conditions, the initial data is not conformally flat. This has one important consequence, which is, as I said, in the black hole binary problem, the singularity is hidden in this one variable, scalar variable, and the other functions are smooth. So this is no longer the case. So all our functions have a singularity, right? So it's not just that the singularity is extended, it's just that it's present in all your functions. So this makes it considerably worse. So one thing that we had to do is, again, modify the gauge evolution equation. And one way to do it is that if you start with, say, coordinates which are not harmonic on the spatial slices, then we want to drive our gauge to harmonic coordinates on the spatial slices. So one has to add these terms together with some function that controls the various scales involved in the horizon and the time scales as well. And this type of evolution equation drives the coordinates to harmonic coordinates on the slices. And these are good coordinates. If you don't do that, then this equation will basically drive your coordinates to the initial ones in exponentially fast time scale. And this is not good, because then, well, you may develop coordinate singularities. Yes?
So I guess I don't quite understand the algorithm, because adaptive mesh refinement basically says, I'm going to add a whole bunch of points, whenever the truncation error is needed. But, the sort of moving puncture type strategy basically, requires that everything inside the horizon is massively under-resolved.
Yes.
So is there like a switch or something that says, by the way, in this region, don't bother to refine anything?
Well, no, I mean, you need to resolve that region which covers the horizon, right? So you need to have the horizon well resolved.
But the region between, say, the horizon and whatever, other asymptotically flat ends or something is massively under-resolved.
No. And that's precisely what having a mesh hierarchy achieves, that you have the right resolution at the right scales. So at the horizon, you need, of course, more levels, as we saw earlier, because your gradients of your functions are steeper there, right? But as you move away from the black hole, then you don't need as much resolution, right? Because the functions just decay. So, and it turns out that, again, using this trigger function, this works well in terms of providing a good resolution in different areas, on different scales. And, well, you can run your convergence tests and so on to make sure that that's the case. So I don't know if this addresses your question.
Well, I mean, so if you think about, say, the binary black hole stuff, the SSM, what you find is that it massively fails a convergence test everywhere inside the horizon, but you
Sure.
don't care because that doesn't include any of the stuff outside the horizon.
Sure, that's.
What you need. So is that also?
It's the same, absolutely, absolutely. And you will see right in the next slide what we actually do in this region, which is under-resolved, and how we deal with it.
Okay, good. That's what I wanted to know.
Yeah.
Sorry for getting.
No, absolutely. That's absolutely fine. Yes.
In that case, because you only have wormhole slices.
We have, sorry?
In the SSM, moving function, it's
Yes.
always wormhole slices. What is the topology of your spatial slices here?
It's the same. It's trivial.
So it's also like it has a throat.
Yes.
It comes out the other side. It's
Yes.
the same.
Yes. That's exactly the same. Yes. So just addressing this issue is precisely inside the horizon. There's a singularity. It's a coordinate singularity. It's an asymptotic region. It's not a physical singularity, but it's a singularity nevertheless. So you have to do something with it. So what we do is that since the features are under-resolved anyway, we smooth out our functions by introducing diffusion terms. And this doesn't matter. So in a sense, we change the Einstein equations in this region, introducing a diffusion term, which is totally artificial and unphysical, which what it does is to basically smooth out the functions and avoid and keeping these errors under control so that they don't blow up in finite time. And what we do is to add a term like this to the evolution equation of this variable. The reason is that this is the only variable that appears with second derivatives in the equations of motion, except for the gauge functions. Okay? So first you have to add it like a traceless term, because you want the determinant to stay to 1. So that's why you add this term. And then here you add a trigger function that turns on this term in the right region. So this trigger function basically depends on this function chi, because as I said earlier, it tracks the apparent horizon in our coordinates. So we choose a contour of this function which is well inside the apparent horizon to make sure that we only modify the equations of motion in the region which we are under resolving the solution anyway, right? So our numerical solution is bad there, so we just change the equations there anyway to make sure that these functions stay smooth. And also, of course, the gradients of these are important to kind of know that you are within the region. So just to give you an example of these terms, so this is a snapshot of one of these like unstable rings after it has evolved for a while. Then this is the shape of the apparent horizon, and this is the region where we turn on this term, right? So this, you can morally understand this as some kind of excision, right? So we just change the equations in a region which is well inside the apparent horizon. So in practice, what one does is, well, you run the same simulation with different values of these, cutoff parameters, so that to make sure that you are within the apparent horizon and you don't modify the physics on and outside the apparent horizon, which is all you care about at the end of the day. Okay, so that's how we do it. I hope that this addresses your question.
Yeah, I mean, it does, although I'm still curious, just because on the face of it, this sounds much more involved. I mean, why do this as opposed to just doing excision?
Well, you will see that in a second as well, why you need to do it this way, which is the fact that in these dynamics of these black holes, the apparent horizon is no longer star-shaped surface. So what do I mean by that? So yeah, so just to keep things simple, so suppose that you have a spherical surface. I'll just suppress the azimuthal direction. So that's a typical situation in the black hole binary problem, where you want to find the apparent horizon, which is a sphere. So you can just find it by just making this assumption that each point on the surface is just given by just the angle, right, the pole angle. So that works well, and this is how it's done in the black hole binary problem. However, in these rings or in these spherical black holes, we will see in a second, then you often encounter surfaces of with these shapes. So this surface is no longer a star-shaped surface, because basically this function is no longer single-valued. So you cannot find the apparent horizon using the traditional approach, which is basically gives you an elliptic equation for a function. Okay. So what do we do in this situation? So first, one option is to use a parametric version of the surface, and then you look for a surface whose outgoing null geodesics have zero expansion. But then you have a parameter on the surface, so you need to provide another equation for this parameter to close the system. And one way that we did it is just to choose some kind of harmonic coordinates on the surface, and then you can show that the resulting system is elliptic, which you can solve using just a standard techniques. And as part of excision, then this is linked to solving this problem is part of your evolution scheme. But this is difficult. Our method turned out to be quite unstable. So in the end, it became a bit of black art to kind of find these surfaces. And I think when your method becomes black magic, pretty much, then it's really not good. So that's one, because we encountered this type of very extreme surfaces, doing excision is difficult and it's expensive. So that's why we choose the other evolution scheme, where finding the surfaces is decoupled from the actual evolution. But in principle, you could do it, but you need to find an efficient way of finding these surfaces. More recently, these authors have proposed the use of reference surfaces, where you basically just choose your surface, which you can parameterize in whichever you like, and as long as the normals from this surface to the actual surface that you are seeking just intersect once and only once, then you can show that these resulting equations are manifestly elliptic. So this seems to be a much better, more robust approach. Moreover, as I said, in our simulations, this function chi tracks the apparent horizon. So the contours of this function would provide very good reference surfaces. So this, I think, seems to be a very promising way to implement excision in this case, but we have not done it yet. But I think that's something which is worth thinking about. So, okay. So that's basically the main difficulties that we encounter. So now let me show you some of these dynamics that I've been telling you. So here it's just an example of one of these rings on the rotation plane. That's the apparent horizon. We perturb it with some perturbation that breaks the symmetry along the rotation plane, and we just solve the equations. And this is what these rings do. They develop these crazy shapes, and here you can see that this sequence of like big bulges connected by long necks, that's just a reflection of the Gregola Flamm dynamics. Also, you see this like clear square. This is because there exists another sector of perturbations, which is not of the Gregola Flamm type. Of course, nonlinearly, both are excited and both coexist, and it depends on your choice of initial conditions which one is going to win. In this case, it turns out that the Gregola Flamm sector grows fastest and dominates the nonlinear dynamics. So if you follow the evolution further, then this surface becomes even more extreme, and well, that's as far as we could get in this case. But you here clearly see this sequence of big bulges connected by long necks. So those are very well approximated by black strings, which we know from the work of Louise and Franz that they are unstable, and the development of these instabilities is very fast, exponential in fact. Whilst this object is of course radiating gravitational waves, the latter only happens on a timescale which follows a power law. So that the Gregola Flamm dynamics is much faster than gravitational radiation. So once these objects reach this point, then their fate is sealed. So they are going to form a singularity in finite asymptotic time before it has had time to collapse. Again, this is asymptotically flat, 5 dimensions. So another example that we looked at was these 6-dimensional black holes. So we only consider for simplicity the case where these black holes rotate in a single plane. And we considered perturbations that do not break the rotational symmetry, but they just introduce like oscillations in the radial direction. So effectively, the problem becomes 2 + 1 dimensional, which is much easier, at least computationally initially. So again, the story is the same. So this is just a section of this spherical horizon. So you perturb it a little bit, and yeah, well, for some time not much happens because the perturbation is small. So it takes time for the exponential factor to become large. But eventually you see that these kind of becoming thin along the axis of rotation. And now you will see that it will stop, well, time will go more slowly. So you see that this object wants to evolve into a ring, but the hole in the middle is filled by this membrane, which is very thin, and itself is unstable with some Gregola Flamm type instability, and it forms this sequence of concentric rings connected by thin pieces of membrane, which undergo this local Gregola Flamm dynamics. And well, in fact, in this case, well, you can see this sequence. So it's interesting to note that the actual structures that form here, apart from just repeating themselves on various scales, they actually look very much like the structure here looks very much like the structures you see in columns of fluid when they pinch off. And well, for this particular case, turns out that we managed to get membranes with like 10,000 times thinner than the original black hole. We ended up running with like 22 levels. So the simulation in the end became quite expensive, even as expensive as a 3 + 1 simulation. But again, once you reach this point, you know that these objects are going to pinch and form a singularity in finite time. OK. I have 5 minutes, so I won't tell you about ADS, but I'm not sure if I have time. So I could stop here, or I could just go on for 5 minutes quickly.
You got 5 minutes.
OK, then let me. It will be quick. So OK, so let's change gears now. Move to ADS. So what is this space that I've been talking about? So this is just the Lorentzian version of hyperbolic space. And you can just depict it as a cylinder where time just goes up, and the cylinder has a boundary. Okay? And the metric on the boundary is conformal to R cross Sn. All right? So this region here is the region covered by the Poincare coordinates, which are just the same ones, pretty much, as the ones Poincare coordinates for the hyperbolic space. So why we care about these spaces, and the reason is this conjecture by Maldacena is like 20 years old, which states in a certain limit that general relativity in these spaces is equivalent to a certain quantum field theory, which is actually known what quantum field theory this is, and is in fact very similar to just the ordinary quantum field theories that one observes in nature. So this conjecture, so moreover, that's the equivalence works when here you have gravity, when this is strongly interacting. So this conjecture, even though it seems crazy, after more than 20 years, it's been checked in multiple limits, and it seems to be correct. At least it seems to hold in some version of it. And this is important because making any calculations in strongly interacting quantum field theories is extremely hard, and the methods in quantum field theory basically are very limited. In particular, if you want to consider out of equilibrium situations. And these are relevant in, say, current particle accelerators. So if you can solve the Einstein equations in these spaces, you can learn about the dynamics of strongly interacting quantum field theories, and this has been quite successful, as I said, to correctly interpret some of the experiments that have happened at the LHC or at RIC in the past 20 years. So one subtlety when one wants to solve the Einstein equation here is that ADS is not globally hyperbolic. So if you set up initial conditions on a Cauchy surface, then you only can predict part of the space. The rest of the space is in causal contact with the boundary, so you need to provide boundary conditions as well to construct the full spacetimes to the future of your initial data surface. So that's why I said earlier that in ADS, having approximate boundary conditions is not optional. You have to impose the correct boundary conditions if you want to solve the problem. And it's been conjectured that for reflective boundary conditions, which are the most commonly used, then ADS itself should be unstable to the formation of black holes. And there's evidence for this, numerical evidence in spherical symmetry. These authors considered collapse of a scalar field in spherical symmetry, and they found that for open sets of initial conditions, no matter how small the amplitude of the scalar field was, you ended up forming a black hole if you waited long enough. There's been a lot of work in terms of understanding this, and and there's a rigorous proof for the case of Einstein null dust, that in fact these spaces are unstable. So what we wanted to do is to study this problem beyond spherical symmetry. And our approach was first use generalized harmonic coordinates, precisely because we have a good understanding of the right boundary conditions in these coordinates. And secondly, we use Cartesian coordinates. So the advantage of doing Cartesian coordinates is first because we can use the existing AMR infrastructures. And if your space is nonlinearly unstable, you have a strong UV cascade. So you need this. And second, it avoids problems with having to choose a ridiculously small CFL condition at the origin. The disadvantage is that the boundary is a Lego sphere, but it turns out that, again, that's not a problem in practice because we understand the boundary conditions there, and the fact that we have to throw away part of the domain is also not an issue. So I will just skip the details just to say that one can understand this analytically, and it works once you pose the boundary conditions. And now we have a full 3+1 code that can simulate dynamics in ADS with no symmetry assumptions. So this is just an example. I'm showing here a scalar field, small data, and that's a slice on the xy plane. So the boundary of ADS is the boundary you have here. And once you can see that this is like a Lego sphere, but again, because we understand the right boundary conditions there, we can obtain stable evolutions without any symmetry assumptions. And well, so this just goes on, and well, we didn't run it for long enough to see the formation of a black hole in this case. But I want to emphasize that in ADS, these UV cascades, especially when you drop spherical symmetry, you should expect that you will form black holes or regions of strong curvature in just random places in the domain. So that's one of the main difficulties in simulating the dynamics of the Einstein equations in ADS. And since I'm just running out of time, just I'll quickly summarize. I hope that I've illustrated the fact that once you sort of go beyond astrophysical settings, then you encounter this large separation of scales and strong UV cascades. That's the main challenges that one has to face. In ADS, on top, one has to impose boundary conditions, and it means that you have to bring infinity at some finite coordinate distance and then impose boundary conditions which are compatible with the evolution. And moreover, you encounter linear and nonlinear instabilities, so naked singularities and all of these things. stop here. Thank you.